Good evening, everyone. Myself Sana Sheikh, a second year PhD student at IIT Bombay, and I am a TA of NPTEL course. The course name is Symmetry, stereochemistry and Applications, and the course instructor is Professor Anshuman Roy Chaudhary from So today is week 10 live session. All of you know that on every Monday from 7 to 9 p.m. we are having a live session in which we are discussing the previous year assignment questions of this course. In today's session we are going to discuss the problem based on Diels-Alder reactions. Let's start the today's section. So here we have a question number 1. The question number 1 is predict the products in the following reaction. So you can see here this is an example of dyne and dienophile reaction, which means it is a Diels-Alder reaction. So before starting the question answer session, I would like to give a brief introduction about this topic. This reaction is invented in 1928 by a German scientist. That is the name of the scientist was Otto Diels and Kurt Alder. That's why the name is become Diels-Alder. They have discovered that the alkyne or alkenes with electron withdrawing group add to a conjugated dyne to form a six-membered ring. So here you can see that we have a dyne here, and this is a dienophile. So this is a 4 plus 2 cycloaddition reaction as a ring is formed by an introduction of 2 sigma bond and breaking of pi bond. Here you can see that if we will draw the product, you will observe that 2 sigma bond formation is taking place and breaking of this pi bond is taking place. That's why it's known as 4 plus 2 cycloaddition reaction. So after the time, with the time, the modification of Diels-Alder reaction is also taking place. So some modification have done. Based on that modification, we have different types of substrates. So I will discuss here those substrates. So in this question, you can see we have electron donating group on dyne substrate. Dyne substrate. That means here we have, this is our dyne. I will write here. This is our dyne, and this is our dienophile. Correct? So when we have electron donating group present in dyne and electron withdrawing group present on dienophile, then what will happen? This is a modification of Diels-Alder reaction. So here it will give a partial positive charge on this carbon atom, correct? Because it's electron donating group, and partial negative charge will be here this way, right? This way. While talking about the dienophile, you can see here it's a electron withdrawing group, correct? Electron withdrawing group. This one is the electron withdrawing group, and this one is the electron donating group. Electron donating group. So when because it will electron deficient, so here you will observe the partial negative charge here and partial positive charge here, correct? Now How will be the bonding will takes place here? Anyone? Which will be our major product? Because here we have positive charge, here negative charge. So they will interact with each other to give a desired product. To give a product. So it will attack here. It will go. This bond will go here. This will go here. And this will. Okay. So we will get here product as a 6-member cyclic ring along with the ortho substitution. Ortho substitution. So OMe group will come over here. This withdrawing group will be here, CHO aldehyde group here, and as I told you here, two new sigma bond formation will take place because it's a 4+2 cycloaddition reaction and a Diels-Alder reaction. So here we are getting here two sigma bonds, this one and this one. Now pi bond breaking will take place here. This pi bond will be break, and these two pi bond will also break, and here new pi bond formation will take place at this position. So this will be your product, final product for this substrate. So I hope all of you are clear. This is a Diels-Alder reaction, and here you can see the regioselective reaction because selectivity is there. Regioselectivity is present here. So this is a product for this type of Diels-Alder reaction. Now let's talk about the next one. Yeah. Here you can see that again we have a diene and dienophile. Which one is our diene and which one is dienophile? Sorry, again this is our diene and this is our dienophile. Dienophile, right? But what's the difference between this example and the previous one? In previous example, we have electron donating group here at first carbon position, but here we have at second carbon electron donating group. So what will be the product? See, because we have electron donating group here, so here we will have partial positive charge, correct? Partial positive charge will come here. This is a partial negative charge. Negative charge. Then here again we have partial negative charge. Then here partial positive charge. Okay. While talking about this one again, here we have negative charge, right? Partial negative charge. Same as previous case. In previous case, you can see here we have a negative charge here and positive one is here. Positive. So here also we have the same thing, but now how it will attack? See here, it's a negative charge, so it cannot attack on again a negative charge species. So it will attack over this carbon atom, right? And this carbon will attack on here. This carbon, this bond will shift here, and this will go here like this. So we will get here 6-member cyclic ring, but invert stereochemistry as given here. Invert means O methoxy group will be remain on its own position, its actual position, but CHO will shift here. It will go here, opposite side because of this reaction. So either you can write it this way, or you can write directly by inverting the dienophile or dine, either way you can write. So if you will write this way, it will be easier to understand for you also, because you have to keep one positive charge and one negative charge on one side. When it become both the negative charge, you cannot do the reaction on this way. So that's why you can write this way. It will attack on this carbon, this will attack here, it will go this way, this way, right? So this is the transition state, and you will get this one as a major product. This one is a major product of the reaction. I hope you are getting clear with these examples. So this was 1,2 product. This one is 1,2 product, and this one is 1,4 product. 1,4 product. This one is 1,4 product. Correct? Now the third question is question number 1, third example. Here again you have given the dienophile and diene. So here, but the difference is there here only. Here is your dienophile is the same thing, same as the previous case, but diene is cyclic ring. Your diene is cyclic ring. So how it will react? How it will react? Yeah. See, again the same thing you have to follow. This is your diene. You have to identify your diene and dienophile. When two double bonds are present, that means it's your diene, and if one double bond is present, that means it's your dienophile. So most of the cases dienophile have electron withdrawing group, and diene have electron donating group. So here the same case we have, diene contains the electron donating group and dienophile contains the electron withdrawing group. So as I told you in previous cases, you can do the here resonance structure you can draw, and you can find out the partial positive or negative charge on the particular carbon atom. So here you can see this is a partial positive charge, because it's this carbon is connected to the electron withdrawing group here. That's why here positive charge. Then this way is, we will move this way, and here it's negative, then again positive, then negative. Correct? Negative here. And while talking about this one, here we have negative, here positive. Correct? What will be the product now? It will attack on this carbon. This will move here. This will move here. And this way. Correct? So you will get here 6-member cyclic ring formation. That means the two new sigma bond formation will take place in this reaction, along with the breaking of 3 pi bond and formation of one new pi bond. So the product will be like this. OMe. OMe group will be present on bridging position. Bridging position. And here we have CHO. Now CHO is present here. So its endo will be a major product. Endo product will be major product because secondary orbital of the carbonyl group will overlap with this diene. That's why the endo product will be your major product. Okay, all of you understood? Endo product will be a major product. So this is a front side. This hydrogen will be present here also. This is the front side, and this will be on below the plane. So this will give a major product. Endo product. Because of secondary orbital interaction, this product is major. Okay. Now next one. Here also the same question is that again dienophile and diene. Everywhere you can observe here, everywhere you have a same question, just the substituent is different. So you can do it by yourself also, but here I am going to solve this type of question. Then you can solve a similar type of question by yourself by understanding the concept behind these questions. So here we have a diene, and diene contains an electron donating group. You have to find out the electron donating group present in diene. So all of you know that is a methoxy group, electron withdrawing group, and in dienophile, which one is electron withdrawing group? This is your dienophile. Correct? Here we have ester group. This ester group is electron withdrawing group because carbonyl group, carbon atom is present in this substrate dienophile. That's why it's a electron withdrawing group. It's a electron withdrawing group. And this one is the electron donating group. Okay. Now, how the reaction will proceed? You have to give the positive and negative charge to the carbon atom, then only it will become easy to understand. So here positive charge, then here it will be negative one, correct? Negative, then negative, then again positive, partial positive charge. And here, because it's this carbon is next to the carbonyl carbon atom, because carbonyl carbon are electron withdrawing group, so here partial negative charge will come. Partial negative charge will come over here, and this one is partial positive charge. Now do the same reaction which we were doing earlier. This bond will go here. This carbon will attack on this carbon atom, and this double pi bond will shift here, then this way, and it will attack on this carbon. So we will get directly the product, 6-member cyclic product. This is the product you will get from this reaction. So you can write in another form also. I will write here similar form. Okay, so this will be a product. So this is a 1,4 product. In previous case, we again got endo and 1,2 product. 1,2 product. Here we got. Here we have 1,4 product. And again we will get endo product because of secondary orbital interaction. So this will be also your endo product only. This is front proton. There also it will be on front side. Okay. So 1,4 product formation will take place in this type of reaction. So I hope from previous 4 examples we have clear with the diene and dienophile interaction and Diels-Alder reaction, which is nothing but the 4 plus cycloaddition reaction. Now we will move to the another type of cycloaddition reaction, which is 2 plus 2 cycloaddition reaction. So here you can see that in 2 plus for in previous cases you have seen that for 4 plus 2 cycloaddition reaction we have 4 pi electron and 2 pi electron in dienophile. Then it's become 4 plus 2 cycloaddition reaction. Similarly, in case of 2 plus 2 cycloaddition reaction, we have 2 pi electron here and 2 pi electron in our another dienophile. So here we will do the reaction with 2 plus 2 cycloaddition reaction. So here we will see here this is partial negative charge. Negative charge will come over here and positive charge will be here, right? And while talking about this one, because it's a donating group, electron donating group, so here partial positive charge will generate over here, and here we have a negative charge, negative positive, right? Negative and positive. Now from because here this dienophile is going to participate in the reaction, this double bond and this double bond, both are pi bond. So that's why this nucleophile, which is here, negative charge will attack on this carbon atom, and this oxygen, because it's a strong nucleophile oxygen, O minus will attack on this carbon atom to give a 4-member cyclic ring. So because they are interacting revert, so I will write in this manner, so it will become easy to understand for you. OME, or you can write in a different other way also, like I will write here. Directly I will write OME. I will revert this group instead of that one. OME and here methyl. Then plus we have to remain this group as it is. Here double bond O and M. Correct? Now when 2 plus 2 cycloaddition reaction will take place, what we will get here? 4-member cyclic ring. First of all, 4-member cyclic ring. Correct? Now, here we have oxygen. In 4-member cyclic ring, we have oxygen at one corner. I will draw here oxygen, then this way, and this is the 4-member cyclic ring. Now we will put the substituent on this ring. So first of all, this pi bond is getting getting break here, and 2 new sigma bond formation is taking place. This one and this one. Correct? The reaction is taking place this way, and this one, right? So here we have methyl substituent, right? Methyl substituent present, and here we have one carbon, then methoxy. This carbon is there. Remember this one. This carbon and methoxy group. Correct? So this is the product, major product formed in this reaction. This is the major product forming this reaction. Clear? This is a type of 2+2 cycloaddition reaction. So I hope all of you are clear with this example also. Try to do yourself by reverting the stereochemistry or with the similar type of other examples. So this is the product formed during this reaction. Now let's move to the next question. Again we have 2+2 cycloaddition reaction. Here we will find out the actual product forming in this reaction. So again you have to write the same way. Like now you can see here, this is not a 2+2 cycloaddition reaction because here we have 2 pi bonds. 2 pi bonds means it's a diene. It can react as a diene, and here we have a 1 pi bond. So it will undergo 4+2 cycloaddition reaction. 4+2 because we have 4 pi electrons here, and here we have 2. So it will undergo 4+2 cycloaddition reaction. So now we will see how it's reacting. For simplicity, you can write this way also. Then it will become simple. Okay, I will write directly other form. Yeah, okay, you will not understand. So I am writing this way. Please try to understand. This carbonyl group is, I have just rotated this carbon bond. So carbonyl group came here and methyl group is here. Everything is remain same, right? Is it same or not? Right? It's same, and it's similar to this one also. Correct? Is it or not? Same, right? All 3 structures are same. Just you have to draw in your convenient way. I have drawn this like this for your better understanding. All these structures are same. Now I am writing the this pi bond, heterocyclic pi bond. Now here we have methyl group, and here we have phenyl. Okay. Now how the reaction will take place? Here we have negatively charged oxygen. Of course, the oxygen atom is there, so it will attack on this carbon atom because this nitrogen is electron rich group, electron donating group. So partial positive charge will come on this carbon atom. So that's why oxygen will attack on this carbon only. And this lone pair, not lone pair, this bond breaking will take place, and nitrogen will attack on this carbon atom, and this bond will go this way and this way. Okay. So at final you will get the product You don't have to do anything, just you have to draw the two sigma bonds which form during the reaction. So here we have nitrogen, correct? Nitrogen have phenyl group. Here we have methyl group, correct? I'm not doing anything, I'm just writing new sigma bonds which form during the reaction. Everything is same as it is. That's why I have written in simplest way for better understanding and for writing a better product, easily writing a product. That's why I have written in this way. So now all of you we got this product. All of you know how we got this product. Try by yourself, then it will be good for you, for your practice. Okay. So we got this as a product. I hope this example is also clear to you. This is a 4+2 cycloaddition reaction. Okay, now move to the next question. This is the question number 2 of the assignment. Here the question is predict the product and write the possible mechanism in support of the predicted product. So first we have to find out the product, then we have to write the mechanism for the product formation. So as all of you can see here, we have acidic condition. On arrow you can see H plus and H2O, that means it is a acidic condition. And you can see in the substrate also we have two ketone group, carbonyl group. That means it can undergo a aldol reaction. It's a aldol condensation reaction. And because we have acidic condition, so this one is a acid catalyzed aldol condensation. So in this type of reaction, what happens first? The step 1 in acid catalyzed aldol condensation is step 1. I will write here step 1 of this type of reaction is protonation of an aldehyde or ketone, whichever is present, led to the formation of an enol. So here we have aldehyde as well as ketone. So we will do the protonation of any group, either aldehyde or ketone. So if I will, because we have here different types of substrate, because it's not same substrate is not undergoing aldol condensation. That's why, because we have the two different substrate, so this reaction will give a cross product. Cross products. I will tell you how it will give a cross product. So first of all, we have to go step by step. So because as I told you, it will protonate the aldehyde or ketone to form the enol. So in first case, I am going to protonate this ketone. Then in second case, I will protonate the aldehyde. So when I will protonate the ketone, I will protonate the ketone here, H3O. H plus H2 is nothing but H3O, or we can say acidic medium, acidic condition. Okay. Because aldol reactions are highly reversible, that's why we are writing this way. Reversible arrow is writing here. We are writing reversible arrow because it's a reversible reaction. So protonation will take place and double bond O H we will get here because protonation is taking place here. And this is CH3, CH2, sorry, CH3, CH2, CH3. Okay. Then enolate will form here. Enol formation will take place. So We have here H2O, water, which will abstract the proton. Suppose we have this intermediate CH3, H is here, sorry, both structures are same. I am just writing in a different way. O H. This bond breaking is taking place to give a positive charge over here. Correct? Positive charge. And here we have CH3 group again. CH3. Now what will happen? Water will abstract the proton, this one, and we will get enol. CH3 double bond OH enol. This is the first step. This is the first step of the reaction. Now what will happen in second step? Here we got the enol. Enol. Now in second step, enol adds to another protonated aldehyde or ketone. So here we have another substrate because it's we have a cross condensation, so that's why we have a different substrate. So this enol now attack on a protonated aldehyde. This aldehyde will get protonated. I will write here protonated one plus C double bond OH protonated aldehyde. Correct? This is a protonated aldehyde. Now this enol will attack on this one. This this enol will attack on protonated aldehyde carbonyl carbon, and this will go like this. And the arrow pushing will go like this way to give a corresponding product. I will write here C double bond OH CH3 CH This was the enol. This was the enol. I'm writing this way. Okay. And it attacks on this carbon atom. So I'm writing now this was the enol part and this CH has attacked on this carbonyl carbon atom. So now I will write carbonyl carbon which is attached to OH group, this OH group, and then CH3. Okay, here hydrogen. So this is a resonance stabilized structure of this molecule. Resonance stabilized structure. Now it will undergo a third step where deprotonation of intermediate will take place. Deprotonation of intermediate. So here this proton will be abstracted by again water and H2O, the proton will go this way and we will get the aldol product. I will write here C double bond O CH3 CH CH3 COH CH3 and H. So this is the product. So in this form, if we will write here, this is our CH3 carbonyl. Okay, I will write in the simplest way, not this way. Here we have CH3 carbonyl, same way carbonyl. Now here again we have CH3, this one CH3, because this carbon is going to react with this carbonyl carbon. That's why I have written in this way CH3. Then this is the carbonyl carbon. Here we have OH, OH, and this is CH3. Got it? So this is the one product formed by the aldol condensation reaction in acidic medium. But because we have here aldehyde and ketone both, so here we have a chances of cross product. Cross product formation. That means this enol will attack on this carbon to give a another product. So here I am writing directly a product, but I will request you to do it by yourself. And if you have any doubt, difficulty during this doing the mechanism, then you can ask me on YouTube. You have to do the same way. The mechanism will follow the same way, just the difference will be here. Instead of the ketone, here you have to protonate the aldehyde, and then aldehydic enol formation will take place. Enol of aldehyde will form here, and then enol of aldehyde will attack on ketone carbonyl carbon atom. carbonyl carbon atom of ketone, and it will give you the another cross product. So I am writing the product for the for that one cross product. Here we have CH3. Sorry, you have to mention everything clearly, right? So what will be the cross product? Any guesses? Yeah, if enol will form here and it will attack on this carbon atom. So this will become your alcohol. I will write that directly here. Here OH. You have to do it by yourself. If you are finding any difficulty, then I am going to discuss it in details. You just have to do here protonation of aldehyde instead of ketone. Here you have CH3. So I will write clearly here. Not, I think there is no space to write the product. Aldehyde. Here we have CH3 and this is CH2 CH3. Okay, so this is the second product. This is the second product. This one is the first product. So there are two possible way of writing a product. Both are correct. So you have to do one by yourself, mechanism by yourself. I hope this one is clear to you. Now we can move to the next question. So here also we have a same aldol condensation, but the only difference is that here you can see we have basic condition. We have basic condition. So this reaction is an example of base catalyzed aldol condensation. Correct? Okay. So for base catalyzed aldol condensation reaction, the first step is that base removes alpha proton from an aldehyde or a ketone to form an enolate ion. Right? In acidic condition, what we were doing, we were protonating the aldehyde or ketone. Here we have to abstract the proton, alpha proton from aldehyde or ketone. So because here we have only one substrate. In previous cases we have the two substrates, but here we have only one substrate. So there is no possibility of cross product. That means the only one product formation will take place, and here the abstraction of proton will take place only from this substrate because other substrate is not available. So here we have alpha proton, this one, this is the alpha proton, and abstraction of this alpha proton will take place with base. OH minus will abstract the proton. Okay. So what we will get, I am writing here. carbonyl group will remain as it is. This here we will get negative charge because proton is abstracted, and this negative charge will push here it will go like this, arrow pushing, and you will get the corresponding enol here. I am writing enol here. O minus. O minus. Correct? Now, this enol, in second step, this enolate ion adds to another molecule of the same carbonyl group. Because we have only one carbonyl compound, so it will add to another molecule of the same carbonyl group. So I am writing here the same carbonyl group this way. Oxygen, right? Now this enolate will attack on this carbon. This will go this way, and first, sorry, for negative charge of oxygen will attack here this way, and then this double bond will attack on this carbon group to give a. Everywhere I am writing this reversible arrow because this aldol condensation is highly reversible. So we are getting only 50% yield. That's why I am writing this way. So if it gets reacted with the same molecule, double bond O, O minus will be here, and here we will get this way. Okay, this is the intermediate we will get. Then alkox, this is alkoxy. This intermediate is called as alkoxy. Then this O minus will be get protonated, will get protonated to give the corresponding product. OH this way. This is the product from this in this reaction. Clear? I hope you understood the mechanism also. But the yield is only 50% for this type of reaction. Only 50%. Here we are getting only one product, not any cross product. I hope you are clear to this question also. Sorry. The next question is here. Again, the same way, the question is different here. We have discussed the aldol condensation example, but this is a question of Claisen condensation. What is Claisen condensation? In Claisen condensation, we are one ester group is reacting to the other ester group in the same way like enolate is formed and that attack alpha carbon attack on carbonyl carbon to give a corresponding product like aldol condensation. So here also we have the same thing. We have here ketone and esters. So first what we have to do, we have to form enolate. Then enolate, how enolate will form, we have to see here. So for ketone, this ketone, if I will write in this way, I will open it and write this way: phenyl carbonyl and CH2 CH3 sorry CH3. So this proton will be abstracted by base here and it will become phenyl carbonyl sorry CH2 minus CH2 minus. So after abstraction of this proton, this negatively charged carbon atom will attack on ester carbonyl carbon atom. So I am writing here ester carbonyl carbon also. Here C double bond O M E methyl O M E O M E, correct. So it will attack on this carbonyl carbon atom and it will open up like this. Carbonyl carbon CH2 sorry O minus, here methyl group and here OMe. I will write here OMe. Correct? All of you understood till here? Now in next step, this O minus will push here, negative charge will push here and this OMe group will knock out to give a diketone compound PH oxygen Me. So this is the product formed in this type of reaction. So I hope all of you are clear with this one also. This example is clear to you and the mechanism is also clear to you, right? This is a Claisen condensation reaction. Claisen condensation reaction. Okay. Diketone is a product. You are getting here diketone is a product. Now, next and last one is this question. Here you can see that we have diester group and because it's an intramolecular, in one molecular, within one molecule only we have both the ester group. That's why it's named as a Dickman reaction or Dickman condensation. So basically it's a cyclic Claisen condensation which is named as a Dickman reaction or a Dickman condensation. So in this reaction also the same thing will happen. First it will this base will abstract the proton from alpha carbon atom of ester group. Any ester. Here also you can abstract the proton from, but I'm showing here this way. You can try by yourself doing uh, abstraction from this carbon also. Now, when the abstraction will takes place, we will get the intermediate. I'm writing here double bond O. This is your double bond O. O E T. Here we have negatively charged and negative charge. Then we have all groups are same. O E T. Correct. Now in second step, this negative charge will attack on this carbonyl carbon atom and this will go, this pi bond will break here like this. You please understand the arrow pushing and try to do yourself, then it will be better for you. So here we will, how many ring size we will get here? 1, 2, 3, 4, 5. 5-member cyclic ring formation will take place here. 5-member cyclic ring form here. Now this is our ester group, as I told you, COOET, correct? O E T. And here we have OET group attached here, OET group, and along with O minus, O negative charge, because here it will generate O negative, right? Now in next step, this O negative will push here and this ethoxy group will knock out here this way. So what we will get in next step? We will get 5-member cyclic ring along with ester group present here, correct? And carbonyl group present on this carbon atom. This is alpha, this carbon is alpha, this one is beta. So beta carbonyl, beta ketone ester formation will take place in Dickman cyclization reaction. So I hope all of you are understood this question also. So the product in this reaction is beta keto ester. This is our product, beta keto ester. Thank you so much for your kind attention. I will just summarize the today's lecture and then you have to practice yourself. So uh, in uh, in today's lecture we have discussed the previous year week 10 assignment. In week 10 assignment we have discussed about the pericyclic reaction, or we can say a cycloaddition reaction, not pericyclic, it's a cycloaddition reaction. So in cycloaddition reaction we have see that in question number 1 we have to find out the products of the reaction. So the first question was an example of 4 plus 2 cycloaddition reaction, which is also called as Diels-Alder reaction. So we have done the Diels-Alder reaction by assigning the charges on carbon atoms. So here in a Diels-Alder reaction, 2 new sigma bond formation is taking place along with the breaking of 3 pi bonds. So 2 sigma bond formation we have observed here, and breaking of 3 pi bonds and making of 1 new pi bond over here. So first you have to assign the partial positive or negative charge on carbon atom. Then you have to just do the cyclization. Like negative charge will attack on positive charge and it will move here, and it will move to here diene, and this negatively charged carbon atom will attack on this carbon atom CH2 positive carbon atom, and this is your dienophile. Dienophile contains your electron withdrawing group and diene contains a electron donating group. So this is a 4 plus 2 cycloaddition reaction. In next question we have seen the same similar example. The only difference was that the methoxy group position. So when the methoxy group position is changed, then the partial positive or negative charge on carbon atom also changes. So here you can see that here I have assigned all the charges on carbon atom in previous case also and here also for your better understanding. Please do it yourself also to know how it's going to react with the dinophile. Now this negative charge will attack the CH2 of dinophile, and the negatively charged carbon atom will attack on this the double bond of diene. So here you can see how the arrow pushing is going and to give the this 1,4 product. In previous case we got the 1,2 product. Here we got the 1,4 product. This is also a 4 plus 2 cycloaddition reaction and a Diels-Alder reaction. Now here again the Diels-Alder reaction we have done here and 4 plus 2 cycloaddition reaction, but the difference here is that we have a cyclic diene instead of a open chain diene. So in cyclic diene we observe that the everything we have to do in the similar manner, like we have to assign the charges on carbon atoms, partially positive or negative charges on carbon atoms to proceed the reaction. But along with that, we have observed that here endo product is formed because of the secondary orbital interaction between the pi bond and this carbonyl carbon oxygen pi bond. Because of secondary orbital interaction, this endo product is more stable. So this is the 1,2 product we got here, and bridging carbon atom is this one. In the next case, again we got the bridging carbon atom, two bridging carbon atom, and again we have assigned the partial positive and negative charge on each carbon atom to get the product. Again we observe the endo product is a major product. So this is in this case we got in this case we observe that a 1,4 product formation. So this is the 1,4 product. Then here we observe that this is the type of 2 plus 2 cycloaddition reaction, where we have observed that the for 2 plus 2 cycloaddition reaction also we have done the similar manner, and we have written here positive and partially negative charges on the carbon atom, and we have observed that positive charge can react with the negative one. That's why we have rotated the molecule, and we observe that 4-member cyclic ring formation, which shows this type of geometry and substitution. So this is a type of 2 plus 2 cycloaddition reaction, which include the oxygen in a cycloaddition reaction. Oxygen in a reaction. It's a kind of Paterno-Bucci reaction. Paterno-Bucci reaction is also like this only. You can see that also. Now in this case, we have observed that this is a type of 4 plus 2 cycloaddition reaction. But here a heteroatom is also included in a heterocyclic, we can say heterocyclic reaction, or heteroatom is also included in a 4 plus 2 cycloaddition reaction. So I have written this dinophile in this way for your simplicity, and this is nothing but same as this one. So I have written in simple way. Then it reacted with the dinophile to give a this heterocyclic ring, 6-member heterocyclic ring, which is containing oxygen and nitrogen with one pi bond. So this is your major product in this reaction. Then we move to the mechanism reaction mechanism question, where we have to predict the product and also have to write the possible mechanism to support the predicted product. So here we have observed that this is the aldol type reaction, aldol condensation, but because we have acidic condition, that means it is the acid catalyzed aldol condensation. So in acidic condition, aldol condensation undergo a protonation reaction. So in first step, this any ketone or aldehyde will get protonated. First of all, it will get protonated. Then after protonation, enol will form, and enol will attack on another aldehyde or ketone, to form this intermediate. Then further proton was accepted by water to give this as a product. So the other way is also possible. The protonation can be done on aldehyde also, which will give a this second product. If protonation will done on aldehyde, then it will give this product, and if protonation will done on this ketone, so then it will give this product, this second or first product. So I have shown this mechanism only. This one you have to do by yourself. Then second question, here again we have done the aldol condensation reaction, but it is a base catalyzed reaction. Base catalyzed aldol reaction is proceed via abstraction of proton from alpha position of carbonyl carbon atom. Because here we have only one substrate, that's why there is no cross product formation is taking place, unlike from the previous one. Here we have two products, cross products. Here we don't have any cross product because we have only one substrate. So here alpha proton abstraction will take place, and it will form enolate, and here it will form, and this enolate uh, will undergo reaction with another molecule of the substrate, where this alpha carbon will attack on carbonyl carbon atom to give the corresponding intermediate. Then this O minus will be protonated by solvent to give this as a product. And because it's a reversible reaction, it's only giving a 50% yield. Now then we move to the next question, where we have discussed the Claisen condensation reaction. In Claisen condensation reaction, the abstraction of alpha proton is taking place. So the alpha proton abstracted from ketone here, and then this CH minus attacked on carbonyl carbon atom of ester. Then they form this tetra substituted carbon intermediate. Then after this negatively charged will push here, and this OMe group will knock out to give this corresponding diketone as a product. 1,3-diketone as a product by Claisen condensation reaction. Diketone. Okay. Then at last we have discussed the again Claisen condensation type reaction, but because it is intramolecular within a molecule only, that's why it's known as a Dickmann condensation reaction. So here in Dickmann condensation reaction, we have observed that abstraction of proton is taking place at this position, that is alpha to ester group, alpha of carbon atom from the ester group, and then this negatively charged carbon atom will attack on this carbonyl carbon atom to give a 5-member cyclic ring. Then this negatively charged oxygen atom, negative charge will push here, and this ethoxy group, OET or ethoxy group will knock out to give a beta keto ester as a product. This is a beta keto ester. Sorry. Beta keto ester. So I hope all of you are understood till here. If any doubt, any question, anything is remaining here, and or you have to ask anything, you can ask me on YouTube channel in comment section. Thank you so much for your kind attention. Thank you all.